So the next video is on calculating work when the force is not constant, so when it's changing, and this is from chapter 9-4 in the textbook. Okay, so what if we have, so previously we saw that if we wanted to calculate work from a constant force, it was just force times displacement. Well, and keeping in mind that it's just the parallel component that matters. So, but one way to think about this, so if you make a graph of this parallel component of the force, so that's this F cosine theta, versus the displacement, denoted as L here. So then the work is actually the area underneath here, right? So it's F cos theta times delta L. So the work is the area under the curve. So you could imagine then if you have some changing force, so the force changes over this displacement. So you can imagine slicing this up into little boxes. So you find the area of each one of these little boxes and then you add them all up. So, and then to actually get a better estimate, then you imagine taking those boxes and shrinking their width, this delta L, to smaller and smaller values. So, right, so the work then, it's the sum of this F cos theta, so that's the parallel component, times delta L. Then you shrink delta L down to 0, and hopefully this should start to look rather familiar. This is a Riemann sum. So then you can write this as an integral. So in general then, to calculate work from an arbitrary force, you need to take this parallel component of the force, integrate from start to finish, so from point A to point B here, over the displacement, dl. Now remember, you can also write this in terms of the dot product, because the dot product picks out this parallel component. So you could write this as vector F dotted into the little element of displacement, dl. So, and just a quick reminder here, so you've done this in calculus. So essentially what we're doing, so we're finding the area under the force versus displacement graph, and that's really just a definite integral, right? So integral a to b f dot dr. So now I'm using an r instead of an L for the displacement. Then remember, the fundamental theorem of calculus relates these definite integrals to antiderivatives, because if you have a definite integral, so f of x dx from point A to point B, you can calculate that as capital F of B minus capital F of A, where f is the antiderivative of little f. So df dx is equal to this little f. Okay, so now that we know that, so we can have a general formulation of work. So this works for any force, whether it's changing or not, over any displacement. So to calculate this work, it's going to be our integral from the initial position r sub I to the final position r sub f of the vector force F dotted into the little element of displacement dr. And we could also write this in terms of components. So integral r sub I to r sub f, fx dx plus fy dy plus fc dz.